operations. String constants. The constants defined in this module are string.ascii letters, the concatenation of the ASCII lowercase and ASCII uppercase constants described below. This value is not local dependent. String.ascii lowercase. The lowercase letters A to Z lowercase. This value is not local dependent and will not change. String.ascii underscore uppercase. The uppercase letter A to Z. This value is not local dependent and will not change. String digits. The string 0 to 9. String.hexdit is the string 0 to 9 ABCDEF, ABCDEF capital. String.oct digits, the string 0 1 2 3 4 5 6 7. String punctuation, string of ASCII characters which are considered punctuation characters in the C locale. Exclamation, double inverted comma, hash, dollar sign, percentage, ampersand, single inverted comma, small bracket, asterisk, plus, comma, hyphen, dot, slash, colon, semicolon, less than, equal to, greater than, question mark, at the rate, open square bracket, close square bracket, backslash, x or operator, underscore, apostrophe, comma, open curly brace, close curly brace, or operator, tilde. String.printable, string of ASCII characters which are considered printable. This is a combination of digits, ASCII letters, punctuation, and white space. String.white space, a string containing all ASCII characters that are considered white space. This includes characters, space, tab, line feed, return, form feed, and vertical tab. Custom string formatting. The built-in string class provides the ability to do complex variable substitution and value formatting via the format method described in PEP 3101. The formatter class in the string module allows you to create and customize your own string formatting behaviors using the same implementation as the built-in format method. Class string.formatter. The formatter class has the following public methods: format string, comma, slash, comma, asterisk args, comma, asterisk keyword args. The primary API method, it takes a format string and an arbitrary set of positional and keyword arguments. It is just a wrapper that calls vformat. Changed in version 3.7, a format string argument is now position only. Vformat, format string, comma, args, comma, kwrs. This function does the actual work of formatting. It is exposed as a separate function for cases where you want to pass in a predefined dictionary of arguments rather than unpacking and repacking the dictionary as individual arguments using the pointer args and pointer keyword args syntax. Vformat does the work of breaking up the format string into character data and replacement fields. It calls the various methods described below. In addition, the formatter defines a number of methods that are intended to be replaced by subclasses. Parse format string. Loop over the format string and return an iterable of tuples, literal text, field name, format spec conversion. This is used by vformat to break the string into either literal text or replacement fields. The values in the tuple conceptually represent a span of literal text followed by a single replacement field. If there is no literal text, which can happen if two replacement fields occur consecutively, then literal text will be a zero length string. If there is no replacement field, then the values of field name, format spec conversion will be none. Get field name, comma, rs, comma, kwrs. Given field name as written by parse, see above, convert it to an object to be formatted. Returns a tuple object, comma, used underscore key. The default version text strings of the form defined in PEP 3101, such as 0 name or label.title. Args and kwrs are as passed in vformat. The return value used underscore key has the same meaning as the key parameter to get value. Get value key, comma, rs, comma, kwrs. Retrieve a given field value. The key argument will be either an integer or a string. If it is an integer, it represents the index of the positional argument in Rs. If it is a string, then it represents a named argument in kwrs. The Rs parameter is set to the list of positional arguments to vformat, and the kwrs parameter is set to the dictionary of keyword arguments. For compound field names, these functions are only called for the first component of the field name. Subsequent components are handled through normal attribute and indexing operations. So, for example, the field expression 0.name would cause get value to be called with a key argument of 0. The name attribute will be looked up after get value returns up by the built-in get attribute function. If the index or keyword refers to an item that does not exist, then the index error or key error should be raised. Check underscore unused underscore hours used underscore hours kwr. Implement checking for unused arguments if desired. The arguments to this function is set of all arguments keys that were actually referred to in the format string, integers for positional arguments and strings for named arguments, and a reference to the args and kwrs that was passed to v format. The set of unused args can be calculated from these parameters. Check underscore unused underscore args is assumed to raise an exception if the check fails. Format underscore field value comma format spec. Format underscore field simply calls the global format built-in. This method is provided so that subclass can override it. Convert underscore field value conversion converts the value returned by getField given a conversion type as in the tuple returned by the parse method. The default version understands as a string R repr and a ASCII conversion types. Format string syntax. The str.format method and the formatter class share the same syntax for the format strings, although in the case of formatter, subclasses can define their own format string syntax. The syntax is related to that of formatted string literals, but it is less sophisticated and in particular does not support arbitrary expressions. Format strings contain replacement fields surrounded by curly braces. Anything that is not contained in braces is considered literal text, which is copied unchanged to the output. If you need to include a brace character in the literal text, it can be escaped by doubling curly braces. The grammar for a replacement field is as follows. Replacement field, this is the grammar. You can go through. In less formal terms, the replacement field can start with a field name that specifies the object whose value is to be formatted and inserted into the output instead of the replacement field. The field name is optionally followed by a conversion field, which is preceded by an exclamation point exclamation and a format spec, which is preceded by a colon. These specify a non-default format for the replacement value. See also the format specification mini language section. The field name itself begins with an argument name that is either a number or a keyword. If it's a number, it refers to a positional argument, and if it's a keyword, it refers to a named keyword argument. An argname is treated as a number if a call to str.isDecimal on the string would return true. If the numerical arg underscore names in a format string are 0, 1, 2 in sequence, they can all be omitted, not just some. And the number 0, 1, 2 will be automatically inserted in that order because arg name is not quote delimited. It is not possible to specify arbitrary dictionary keys. Example, the strings 1, 0 or colon hyphen within a format string. The arg name can be followed by any number of index or attribute expression. An expression of the form dot name selects the named attribute using get attribute, while an expression of the form index does an index lookup using get item. Some simple format string examples. First, thou shalt count to 0 references first positional argument. Bring me a pair of braces implicitly references the first positional argument. From first pair of braces to second pair of braces, same as from 0 and 1. My quest is name references keyword argument name. Weight in tons 0 dot weight attribute of first positional argument. Units destroyed players 0 first element of keyword argument players. The conversion field causes a type conversion before formatting. Normally, the job of formatting a value is done by format method of the value itself. However, in some cases, it is desirable to force a type to be formatted as a string, overriding its own definition of formatting. By converting the value to a string before calling format, the normal formatting logic is bypassed. Three conversion flags are currently supported: exclamation s which calls string method on the value, exclamation r which calls rep r method, exclamation a which calls ASCII. See some example. Harold's a clever 0 exclamation s calls str method on the argument first, bring out the holy name, exclamation r calls rep r on the argument first, more, exclamation a calls ASCII on the argument first. For example, print a and this, and then 0 exclamation ASCII, and here dot format, and here let's provide Panchdev a Panchdev. If I say R, like this. If I say name, so I need to provide name. Oh, it should be like name is equal to, okay. The format spec field contains a specification of how the value should be presented, including such details as field width, alignment, padding, decimal precision, and so on. Each value type can define its own formatting mini language or interpretation of the format spec. Most built-in types support a common formatting mini language which is described in the next section. A format spec field can also include nested replacement fields within it. These nested replacement fields may contain a field name, conversion flag, and format specification, but deeper nesting is not allowed. The replacement fields within the format spec are substituted before the format spec string is interpreted. This allows the formatting of a value to be dynamically specified. See some format examples. Here are format examples. You will see format specification mini language. Format specifications are used within replacement fields contained within a format string to define how individual values are presented. See format string syntax f strings. They can also be passed directly to the built-in format function. Each formatable type may define how the format specification is to be interpreted. Most built-in types implement the following options for format specifications, although some of the formatting options are only supported by the numeric types. A general convention is that an empty format specification produces the same result as if you had called string method on the value. A non-empty format specification typically modifies the result. The general form of a standard format specifier is format spec. This one field align sign z hash 0 width grouping option dot p fill any align greater than less than greater than equal xo sign plus minus empty string width digit plus grouping option underscore or comma precision digit plus type b c d e f g G and O. If a valid align value is specified, it can be preceded by a field character that can be any character and defaults to a space if omitted. It is not possible to use a literal curly brace open curly brace or close curly brace as a field character in a formatted string literal, or when using the str.format method. However, it is possible to insert a curly brace with a nested replacement field. This limitation doesn't affect the format function. The meaning of the various alignment options is as follows. Okay, so if you want to print curly brace, you have to do like this. It will print single curly brace, escaping it, and for closing this. Like this. Option meaning less than forces the field to be left aligned within the available space. This is the default for most objects. Greater than forces the field to be right aligned within the available space. This is the default for numbers. Equal forces the padding to be placed after the sign if any but before the digits. This is used for printing fields in the form plus 0000120. This option alignment option is only valid for numeric types. It becomes the default for numbers when 0 immediately precedes the field with. XOR forces the field to be entered within the available space. Note that unless a minimum field width is defined, the field width will always be the same size as the data to fill it, so that the alignment option has no meaning in this case. The sign option is only valid for number types and can be one of the following: plus, minus, or space. Plus indicates that a sign should be used for both positive as well as negative numbers. A minus indicates that a sign should be used only for negative numbers. This is the default behavior. Space indicates that a leading space should be used on positive numbers and a minus sign on negative numbers. The Z option coerces negative 0 floating point values to positive 0 after rounding to the format precision. This option is only valid for floating point presentation types. The hash option causes the alternate form to be used for the conversion. The alternate form is defined definitely for differently for different types. This option is only valid for integer, float, and complex types. For integers, when binary, octal, or hexadecimal output is used, this option adds the respective prefix 0b, 0, 0x, or 0 capital X to the output value. For float and complex, the alternate form causes the result of the conversion to always contain a decimal point character, even if no digits follow it. Normally, a decimal point character appears in the result of these conversions only if a digit follows it. In addition, for G or capital G conversions, trailing zeros are not removed from the result. The comma option signals the use of a comma for a thousand separator. For a local aware separator, use the an integer presentation type instead. The underscore option signals the use of an underscore for a thousand separator for floating point presentation types and for integer presentation type D. For integer presentation types B, O, X, and capital X, underscore will be inserted every 4 digits. For other representation types, specifying this option is an error. Width is a decimal integer defining the minimal total width, including any prefixes, separators, and other formatting characters. If not specified, then the field width will be determined by the content. When no explicit argument is given preceding the width field by a 0 character enables sign aware 0 padding for numeric types. This is equivalent to a field character of 0 with an alignment type of equal. The precision is a decimal integer indicating how many digits should be displayed after the decimal point for presentation types F and F, or before and after decimal point or for presentation types G or capital G. For string presentation types, the field indicates the maximum field size. In other words, how many characters will be used from the field content. The precision is not allowed for integer presentation types. Finally, the type determines how the data should be presented. The available string presentation types are S. String format. This is the default type for strings and may be omitted. None, the same as S. The available integer presentation types are: B. Binary format outputs the number in base 2. C. Character converts the integer to the corresponding Unicode character before printing. D. Decimal integer outputs the number in base 10. O. Octal format outputs the number in base 8. X. Hex format outputs the number in base 16 using lowercase letters for the digit over 9. Capital X hex format outputs the number in base 16 using uppercase letters for the digits above 9. In case hash is specified, the prefix 0x will be uppercase to 0x as well. And number, this is the same as D except that it uses the current local settings to insert the appropriate number separator characters. Non, the same as D. In addition to the above presentation types, integers can be formatted with the floating point presentation types listed below, except n and none. When doing so, float is used to convert the integer to a floating point number before formatting. The available presentation types for float and decimal values are: types, type meaning E. Scientific notation for a given precision P formats the number in scientific notation with the letter E separating the coefficient from the exponent. The coefficient has one digit before and p digits after the decimal point for a total of p plus 1 significant digits. With no precision given, uses a precision of 6 digits after the decimal point for float and shows all coefficient digits for decimal. If no digits follow the decimal point, the decimal point is also removed unless the hash option is used. Capital E scientific notation same as E except it uses an uppercase E as the separator character. F. Fixed point notation. For a given precision P formats the number as a decimal number with exactly P digits following the decimal point. With no precision given, uses a precision of 6 digits after the decimal point for float and uses a precision large enough to show all coefficient digits for decimal. If no digits follow the decimal point is also removed unless the hash option is used. Capital F. Fixed point notation same as F but converts NaN to NaN and INF to INF. General format G. General format for a given precision p greater than equal to 1, this rounds the number to p significant digits and then formats the result in either fixed point format or in scientific notation. Depending on its magnitude, a precision of 0 is treated as equivalent to a precision of 1. The precision rules are as follows. Suppose that the result formatted with presentation type E and precision p minus 1 would have the exponent exp. Then if m less than equal to exp less than p, where m is minus 4 for floats and minus 6 for decimals, the number is formatted with presentation type f and precision p minus 1 minus exp. Otherwise, the number is formatted with presentation type e and precision p minus 1. In both cases, insignificant trailing zeros are removed from the significant and the decimal point is also removed if there are no remaining digits following it, unless the hash option is used. With no precision given, uses a precision of 6 significant digits for float. For decimal, the coefficient of the result is formed from the coefficient digits of the value. Scientific notation is used for values smaller than 1e6 in absolute values and values where the place value of the least significant digit is larger than n, and fixed point notation is used otherwise. Positive and negative infinity, positive and negative 0 and NaNs are formatted as INF minus INF 0 minus 0 and NaN respectively regardless of the precision. Capital G. General format same as G except switches to capital E if the number gets too large. The representations of infinity and NaN are uppercase to n number. This is the same as G except it uses the current local setting to insert the appropriate number separator characters. Percentage multiply multiplies the number by 100 and displays in fixed format followed by a percentage sign. None. The float, this is the same as G except that when fixed point notation is used to format the result, it is always includes at least one digit past the decimal point. The precision used is as large as needed to represent the given value faithfully. For decimal, this is the same as either G or capital G depending on the value of context or capitals for the current decimal context. The overall effect is to match the output of str as altered by the other format modifiers. Format examples. This section contains examples of the str.format syntax and comparison with the old percentage formatting. In most of the cases, the syntax is similar to the old percent hyphen formatting with the addition of braces and with colon used instead of percentage. For example, percentage 03.2f percentage 03.2f can be translated to uh, curly braces colon 03.2f. The new format syntax also supports new and different options shown in the following example. Accessing arguments by position. So this one, accessing arguments by position. A0 will be A, 1 will be replaced by B, C. Okay, ABC. Now this one is also the same. Without any positional indexing. Oh, closing brace, I forget. Okay, then 2 1 0, this can be done. Now CBA and 210 dot format star, unpacking argument sequence, unpacking argument sequence ABC. And 0 ARBA 001, argument indices to be repeated. We can repeat argument indices. Okay, let's put this space. Correct. Accessing arguments by name, coordinates, latitude and latitude. Coordinates, latitude and longitude. Coordinates, latitude and longitude. Coordinates. Coordinates. Coord is equal to okay. This will not work. Dictionary. Here we can see this way. This is the dictionary object. So accessing arguments attributes. C is equal to 3 minus 5j. The complex number 0 is formed from the real part 0 dot real and the imaginary part 0 dot image. C. This is the example. We pass C 0 dot image 0 dot that real. Need to print, so let's print complex number 3 minus 5j is formed from the real part 3.0 and imaginary part minus 5.0. Correct? The class point diff init self xy self dot x is equal to self dot comma self dot y is equal to xy. Diff is string return point self dot x self dot y dot format self. So let's see the example of class. Print and this one point 4 format self is equal to self. Right? Accessing arguments items coordinate 3 5 0 0 0 1 dot format coordinate 3 5 print 0 of 0 0 of 1. Correct? Replacing percentage s and percentage r. The rep r source codes r string doesn't this format test1 test2 print rep r source test1 string doesn't test2. Align the text and specifying width left align. Let's see left align less than 30 left align 30 format left align. Here we can see this is of width 30 and left align less than. Right align, just change the symbol and this will be right align. Right? Centered, just replace this with XOR and this will be now centered. Right? And format centered. Use asterisk as a fill character. Use asterisk as a fill character. Asterisk. So it will be like this. Great. Replacing percentage plus f. Percentage plus f and percentage minus f and percentage f is specifying a sign. So shows it always. Let's do the example. Percentage f, okay. Percentage colon percentage f colon percentage f 3.14. So 3.14 minus plus 3.14 minus 3. Now same shows up space for positive. Let's show the space for positive and negative minus. Then minus shows only the minus no space for positive, minus sign for negative. Replacing percentage x and percentage o and converting the value to different bases. Format also supports binary numbers, integer, so this is 42, 0d in decimal, 0x in hex, 0o in octal, 0b in binary. x2a oct 52 and binary 01101010. Now integer with 0x, okay, has x has o has formatted as o. So the prefix 0o 0x 0b, correct. Now using the comma as a thousand operator, so if I say this colon comma format 1 2 3 4 5, so thousands, okay, and then expressing a percentage, let's define point is equal to this and print points by total percentage 0.2 percentage 86.36 percentage, correct. Using type specific formatting, date time, date time dot date time 2010741215. So percent colon percentage y minus percentage m minus percentage d percentage h percentage m percentage s. So it is 12 15 58. Nesting arguments and more complex examples for align comma tags in zip less than greater than this, left center right 0 fill align 16 dot format text fill align is equal to align, right. Let's do it. Print this one left tag 0 fill is equal to align is equal to align. String of argument octets, this one pointer octets for pointing list colon 02x colon 02x colon 02x. Print octets 02x hexadecimal, right, C088 0001, right. Integer underscore 16, print integer underscore 16, name is not defined. Width is equal to 5 for number in this range, print number in range 5 to 12 for base in dx0b print 0 width and then base format number base is equal to base width is equal to width and is equal to nothing. Template strings. Template strings provide simpler string substitution as described in PEP 292. A primary use case for template strings is for internationalization I-18N since it in that context. Their simpler syntax and functionality makes it easier to translate than other built-in string formatting facilities in Python. As an example of a library built on template strings for I-18N, see the fluffl.i18n package. Template strings support a $based substitution using the following rules. $dollar is an escape. It is replaced with a single dollar. Dollar identifier names a substitution placeholder matching a mapping key of identifier. By default, identifier is restricted to any case and insensitive ASCII alphanumeric string including underscore that starts with an underscore or ASCII letter. The first non-identifier character after the uh, dollar character terminates this placeholder specification. Dollar identifier is a equivalent to dollar identifier. It is required when valid identifier characters follow the placeholder but are not part of the placeholder, such as dollar nounification. Any other appearances of dollar in the string will result in a value error being raised. The string math module provides a template class that implements these rules. The method of templates are string.template template. The constructor takes a single argument which is a template string. Substitution mapping is equal to this slash pointer keywords performs the template substitution returning a new string. Mapping is any dictionary like objects with keys that match the placeholder in the template. Alternatively, you can provide keyword arguments where the keywords are the placeholders. When both mappings and keywords are given and there are duplicates, the placeholders from keywords takes precedence. Safe substitute mapping is equal to these keywords like substitute except that if placeholders are missing from mappings and keywords, instead of raising a key error exception, the original placeholder will appear in the resulting string intact. Also, unlike the substitute, any other appearances of the dollar will simply return dollar instead of raise value error. While other exceptions may still occur, this method is called safe because it always tries to return a usable string instead of raising an exception. In another sense, safe substitute may be anything other than safe since it will silently ignore malformed templates containing dangling delimiters, unmatched braces, or placeholders that are not valid Python identifiers. Is valid returns false if the template has invalid placeholders that will cause substitute to raise value error. Get identifier returns a list of valid identifiers in the template in the order they first appears, ignoring any invalid templates identifiers. Template instances also provide a one public data attribute template. This is the object passed to the constructor's template argument. In general, you shouldn't change it, but read-only access is not enforced. Here is an example of how to use template. From string import template s is equal to template dollar who likes what s dot substitute who team what kung fu pao so pao who likes okay templates s dot substitute and then print print s. So this is as template who likes one as the substitute who team. Mm-hmm. Team likes kung fu. Okay. D is equal to dict who is equal to team. Template give who 100. Substitute D. This will give an error. This will give invalid placeholder is line 1 column 11. Advanced usage. You can derive subclasses of template to customize the placeholder syntax, delimiter character, or the entire regular expression used to pass template strings. To do this, you can override these class attributes. Delimiter. This is the literal string describing a placeholder introducing delimiter. The default value is dollar. Note that this should not be a regular expression, as the implementation will call re.escape on this string as needed. Note further further that you cannot change the delimiter after class creation. A different delimiter must be set in the subclass class namespace. ID pattern. This is the regular expression describing the pattern for non-braced placeholders. The default value is the regular expression question mark a colon start of square bracket underscore a to z and square bracket start of square bracket underscore a to z small 0 to 9 digit end of square bracket star. If this is given and brace ID pattern is none, this pattern will also apply to brace placeholders. Note, since default flags is re.ignore case, pattern A to Z can match with some non-ASCII characters. That's why we use the local A flag here. Brace ID pattern. This is like ID pattern but describes the pattern for braced placeholders. Defaults to none, which means to fall back to ID pattern. The same pattern is used both inside and outside braces. If given, this allows you to define different patterns for braced and unbraced placeholders. Flags. The regular expression flags that will applied when compiling the regular expression used for recognizing substitutions. The default value is re.ignore case. Note that re.verbose will always be added to the flags. So custom ID patterns must follow conventions for verbose regular expressions. Alternatively, you can provide the entire regular expression pattern by overriding the class attribute pattern. If you do this, the value must be a regular expression object with 4 named capturing groups. The capturing groups correspond to the rules given above, along with the invalid placeholder escaped. This group matches the escape sequence $$ in the default pattern. Named. This group matches the unbraced placeholder name. It should not include the delimiter in capturing group. Braced. This group matches the brace and close placeholder name. It should not include either the delimiter or braces in the capturing group. Invalid. This group matches any other delimiter pattern, usually a single delimiter, and it should appear last in the regular expression. The methods on this class will raise value error if the pattern matches the template without one of these named groups matchings. Helper function string.cap words as separator is equal to name. Split the argument into words using str.split. Capitalize each word using str.capitalize and join the capitalized words using str.join. If the optional second argument sep is absent or none, runs on white space characters are replaced by a single space and leading and trailing white space are removed. Otherwise, sep is used to split and join words. Thank you.